local event, so increment this from 0 to 1, and then the last one is to 0. So now we want to receive this message sent by process 1 to process 2. Okay? So how would you get this value? So now let's look at two things. So this is a receiving event, right? So this is kind of an event happening at process 2. So what you do is you first increment your own clock because of the receiving. So you increment this 1 to 2. Okay? And then what you do, you go based on the timestamp of the message. What is the timestamp of the message? The time at which it was sent. The time at which it was sent is 200. That's the timestamp of this message. So what you do essentially now is a component-wise maximum. What you do, what I mean by component-wise maximum, pick up this, because this indicates what? The clock value that P1 thinks is for P1, because basically P1 is sending this. So we take the maximum of 2 and the 0, because 0 is P2's estimate of the clock value at P1. So we take the maximum of 2 and 0, that is 2. We could say we take the maximum of 0 and 2 because it's already incremented from 1 to 2 for the P2, the local process. So that is 2. And then the maximum of this 0 and 0 is 0. So you increment your own clock, but for the other processes, you learn from the message. And the message you are getting may not have information better than what you know, but it may have better than what you know. So that's why I take the maximum. So take the maximum of what is in the message with your own estimate of the other processes. So you are thinking 0 and 0 are the clock values at the other processes, whereas the sender of this message, which is process 1, says that its estimate of the clock value of the other processes, including itself, P1 is 2, P2 is 0, P3 is 0. So take the component-wise maximum between the two. Does it make sense? So the other process is telling you some clock value of the other processes. So you go by, you take the maximum of it. You may know better or that process may know better. So you take the maximum. Okay, so because the clock values are increasing. Okay, from 1, 2, 3 and so on. Alright, so now what happened? Let's look at process 3. It's an internal event. So you just increment the last one because as I said, last entry is for process 3. So it increments its clock value from 0 to 1, so it is 0, 0, 1. And this is now a sending event, so you again increment from 1 to 2, and you don't know anything about the other processes, so others are still 0 and 0, so 0, 0, 2. So this message now has what timestamp? 0, 0, 2. So now tell me how this gets incremented, and you assign that value for this event. What do you do first? Huh? This is a receiving process, right? So what is the entry for the receiving process? The second entry, right? This is process 2, so that's the second number here. So its clock value previously is 2, and you are receiving this message, so you have to first increment that from 2 to 3. And for the other processes, you take the component-wise maximum. You take the maximum of what is this message with what you know currently. So this is 0 and this is 2, so maximum is 2. And then you can say it is 0 and of course 3 now, right? So that is 3. And then maximum of 2 and 0 is 3. So that is the timestamp of this event. So each event will have a timestamp when they occurred, and then the message also carry a timestamp when they were sent. Okay? So let's look at now this event is an internal event, so you just increment your own entry from 2 to 3 and the others also 0. And now let's look at this. This process is sending a message to this process. So how do you assign the timestamp of this message? You is an increment your own scalar and vector, right, from physics. Scalar is one value and vector is like this. It's a collection or math, right? Scalar is one single value integer and vector is a collection of integers. So here we have what is called a vector clock that basically keeps track of the scalar clocks at each process. So each number is still a scalar value indicating the clock value at the individual processes, but every process keeps track of things like this. Okay? Is that clear? So with this, we'll be able to guarantee that. So let's look at some comparisons that we can do with vector clocks. And then we can see how we can guarantee total ordering. So we can say, so each event will now be associated with the timestamps, the vector clock. So like we had here, this event is assigned this vector clock timestamp, this event is given this timestamp, and so on. So each event has now a timestamp, that's basically the vector clock value. So we can say the timestamp, the vector clock, when event A happened is equal to the timestamp when event B happened, provided what event what? All the individual entries are the same. So for example, if this is a timestamp of event A and this is a timestamp of event B, every entry has to be the same. This 2 is equal to 2, this 2 is equal to 2, and so on. So each entry has to be the same as the other clock. Then we can say the two clocks are the same. Is that clear? Now when we say they are not equal, there's at least one entry where the values are not equal. For example, you have 2, 1, 2 and 2, 2, 2. You may have them equal at all the processes except here. You see 1 not equal to 2, the corresponding entry. So if you have at least for one process, so each one is a process, you know that, right? So you have, this means what? There are 3 processes and these are the clock values at 3 processes, P1, P2 and P3. So there's at least one process, that's what I said, at least one PI, in this case P2, where you see the clock value here is 1 and the clock value here is 2 for those events. So you can say 1 is not equal to 2. So because of this, we can say this vector clock value or the timestamp of this event is not equal to the timestamp of this event, because they differ at least in one entry. Okay? Now what is less than or equal? Every value in the first clock timestamp should be less than or equal to every value in the second one. Makes sense, right? When you say A is less than or equal to B, what does it mean? The value of A is less than or equal to B. So here, the component wise, the value should be less than or equal. So 2 is less than or equal to 2, 1 less than or equal to 2, 2 less than or equal to 2. So, makes sense, right? What about strictly less than? Strictly less than means you still have less than or equal to, but at least for one entry you want it to be strictly less than, in the sense that, you see again the same two things. 2 is equal to 2, this 2 is equal to 2, but one entry where you have this 1 here is strictly less than the other one, 2. So at least for one process entry, we should have the value on the first left side should be strictly less than the value on the other one. Okay? So then we can say the timestamp is less than the timestamp of event A is less than the timestamp of event B. Okay? If at least for one entry it is less. Of course the others have to be less than or equal to. Okay? Now finally, what is concurrent? Concurrent means if two events have timestamp like this, we cannot say the timestamp of event A is less than the timestamp of event B, as well as we cannot say the timestamp of event B is less than the timestamp of event A. So we cannot say both. Then we can say A is concurrent to B. How can we do that? For example, you see just two events, the plots 2, 3, 2 and 3, 1, 2. So if you compare them, can you say the first one is less than the second one? You have what? 2, 3, 1 and 3, 1, 2, right? This is less than, but what about this? Is 3 less than 1?
No.
No. So we cannot say 2, 3, 1 is less than 3, 1, 2. right? How about the other way? How about the other way means what? Compare 3, 1, 2 and 2, 3, 1. You cannot say 3 is less than 2, right? So it means you cannot say this is less than this, and you cannot say this is less than this, right? So then only we can say the two events that correspond to these two clock values are concurrent events. See what I mean? So you cannot say the timestamp at which this event occurred is less than the timestamp at which that event occurred, or vice versa. This is the timestamp of event A, this is the timestamp of event B, this is the timestamp of event B, this is the timestamp of event A. We cannot say one timestamp, one clock value is less than the other clock value, either way. So we cannot say whether A happened before B or B happened before A. You see what I mean? So when you cannot say whether A happened before B or B happened before A, then you have to say A is concurrent to B. Okay? Because with this relationship, with this test, you cannot say what A happened before B. The notation that we used earlier. The not and this happened before thing. So because this is not less than this, we say that A, we cannot say whether A happened before B. Similarly, because of this, we cannot say that B happened before A. So we cannot say A happened before B and we cannot say again B happened before B. So the only way we can say or relate the two events is they are concurrent events. Okay? They could occur independent of each other. Concurrent is that's what it is. They are independent of each other. Okay? So let's look at some examples again. The same graph that we worked out earlier, the same kind of, okay, there's a name for it, you might have noticed. So when I give you diagrams like this, there's a time line like this for each process and you do all these things, this is called a space-time diagram. Okay, so remember this name. So this is called a space-time diagram. So the same thing that we did earlier. So now let's do this testing for this concurrency and all these things. So let's take up these two events, E31 and E14. So from this E31 is what? This event, it happened with timestamp 001, and E14 is this one, it happened with timestamp 442. So if you compare them component-wise, 0 is less than 4, this 0 is less than 4, and 1 is less than 2. So every entry is actually less than. And to say this is less than this, all we needed was at least one entry to be less than, the others could be even equal to. Remember we saw in the previous thing that it could be even 2, 1, 2, and this could be 2, 2, 2. We can still say they are less than, because one entry is less than that, the others are equal. But in this case, it's already more than that. It's strictly less than for everything. So we can definitely say what? The event associated with this timestamp happened before the event associated with this timestamp. Okay? So, and you can verify it. How? How you can verify it? Let's do that. So that will lead us to the subsequent topics. This is the event E31, right? That this is the event 14. How we can say this happened before that? After this event happened, you send this message from here to this, right? So after this happened, you send this message from process 3 to process 2, and after receiving this, you send a message from process 2 to process 1. So we can say the first event definitely happened before the other event. So we can prove that. If the clock values like this is less than the clock value of the other one, we can say the first event happened before the say this event happened before this event. And if you look at this, it is true. E12 is sending, you can send a message. And what happens? Then after this event happened. Right? So this event happened before this event. Okay? So this is what we could not say with the scalar, the Lamport clock. Why? Because that was just one integer. Right? So with one integer comparing them we could not say. But here we are comparing what? All the integers. Okay? And what they indicate? They indicate the clock values of the respective processes. Okay? Is that clear? Now let's do this. E11 and E33. If you look at this, the clock values are for E11 is this, 100, and E33 is this. 1 is less than 0. True or not? Not true, right? So we cannot say this just with that first test, 1 less than 0 is not true. So we cannot say this is less than this. This is actually not less than this, right? You cannot say for sure because there may be another entry 0 and 0 and 0 and 3. 0 is less than 3. So, but what about this? 1 and 0? It's not less. Then to compare the other way, 0, this one with this, just 0 is less than 1, fine. 0 is less than 0, fine. But 3 is less than 0, no. So we cannot say this clock value is less than this clock value. So either way we cannot say which is less than the other, which one. Right? So these two events are concurrent events. So if you look at the figure here, this is E11 and this is E33. And you can trace back whether there is a causal relationship between them. E11, you can say I sent a message after this, but do you send anything after that to 3? No. So you cannot trace the path, the relationship from one event to the other event. Okay? You cannot trace something from what? From E11 to E33. You cannot trace a cause and effect relationship like we did for this. Similarly, for the last two, E13 is here, 300, and E23 is here. So if you compare the clock values, 3 is less than 2, no. So we could say this clock value is not less than this. Similarly, comparing this, we can say what? 2 is less than 3, fine, but what about 4 and 0? 4 is not less than 0. So either way, we cannot say which one is less than the other one. So again, the two events are concurrent. Is that clear? So what kind of question you can expect? I'll give you the space-time diagram without the clock value. Just I'll give you what? The messages sent from the processes and some internal events. So what we have to compute, we have to first determine the clock values, vector clock values. I'll give it as the messages like this. Okay? And so first we have to compute the vector clocks like we did. And then I'll give you some event numbers. I'll label those events. So ask you to test whether one event is concurrent with the other event or happened before the other event. Okay? So then you can do comparison like this and find out whether they are causally related or not. What I mean by causally related, these events are causally related. E31 and this event E14 are causally related because one event happened before the other event. But these two events are not causally related because they are concurrent events. It's not like there's no cause and effect relationship. Okay? Is it clear what I mean by cause and effect? This happened because this happened. So that's what is my cause and effect relationship. Okay? Any question? Okay, so now let's start looking at something more interesting. What we did so far is ordering events. It could be local events or sending and receiving events. But now what we want to order is messages. Whether one message was sent before the other message or one message is causally related to another message. Okay? So how to do that? So again, let's look at this moduli example. This tells you the idea behind what is called causal ordering of messages. Let's say this message M1 was sent from here, this event, and it was sent to process 3. Right? And after this message was sent, the same process 1 sends a message M2 to process 2. Right? And after receiving this message, process 2 sends a message to process 3. Right? This M3 is sent by process 2 to process 3. Now you see here, the sending of message 1 happened before what? For sure what? The sending of message 2, right? The sending of message 1 happened before the sending of message 2. And of course now you know that after only you can send, you can receive. So the receive of message 2, the sending of message 2 happened before the receiving of message 2, like this. You can only receive after it was sent. Right? And then what? The receiving of message 2 happened before what? The sending of message 3, this one. The message 3 is sent after message 2 was received. Right? You know the transitive relationship that we saw earlier at the beginning? A happened before B, B happened before C, so A happened before C. Right? So what is here? This happened before this, and this happened before this, and this happened before this. So what can we say from this? All the three things put together. Sending of message 1. Right. Is that clear? Sending of message 1 happened before the sending of message 3. Right? And both M1 and M3 are sent to which process? Both M1 and M3 are sent to which process? Who is receiving? Process 3. Both M1 and M3 are sent to process 3. M1 is sent by process 1 to process 3, and M3 is sent by process 2 to process 3. Right? You see from the figure. I'll tell you, explain that. What is it? But M1 is meant to be sent to process 3, right? Right. And M3 is also meant to be sent to process 3. Isn't it? Mm-hmm. Is that clear so far? Mm-hmm. So, and how they are related? The sending of M1 is what happened before the sending of M3. And both are supposed to be sent to process 3, right? So, if two messages are sent, you send M3 because of sending M1. Right? That's what it may causally related, right? So, is it that the receiving of M1 should happen before the receiving of M3? Supposed to be, right? But you see here, the way the diagram was given to you, the message here is coming, M1 is coming at this time, and M3 arrives to the receiver, process P3 at this time. Right? That's what it is, given to you, right? But you know, since the sending of M1 happened before sending of M3, the delivery of M1 at P3 should happen before the delivery of M3. There's a difference between receiving and delivery. Receiving means it comes to the lower, you have like a network class, but you have a layer of protocols running in a machine. So the lower network interface card has got this message, but it should not be delivered to the application that is supposed to process this message. Okay? So the machine has received that message, but the application is not supposed to process the message. It's not supposed to process until what? Until it gets M1. So the delivery of M1, that's what is the difference between receiving and delivery. You may receive it, but the delivery event should happen after M1 is delivered. So sending of M1 happened before sending of M3, both the same process. So which means the delivery of M1 should happen before what? The delivery of M2 or M3. Right? Do you understand that? So what if you do a transaction? Let me tell that. So let's say you sent $100 or something because of this thing, right? So if you don't get to see why you received M3, you cannot process M3, right? So you need to get M1 first before you go ahead and process M3. Right? Yes.
Is this similar to like SYN and SYN?
What's that?
Like the network protocols, like SYN is SYN of knowledge?
No, that's not.
That's not it?
Yeah.
Sorry.
That's fine. So here you have two events which are sending events which are causally related. So this event, the sending of this message happened before this. So before seeing M1, process 3 cannot do anything on M3. It may look like, why I'm receiving this? You see what I mean? Because all these things happen. Like M1 was sent, and then M2 was sent, and then M3 was sent. So if you first happen to see M3 without looking at M1, you don't know what is this. You see what I mean? So you need to look at the cause first before you look at the effect. So the sending of M3 was the effect of what? The sending of M1. Right? So if both M1 and M3 are delivered to process 3, it has to be delivered in the same order, because then only process 3 can really make use of the two messages. If M3 is delivered first, process 3 cannot make it out why M3 was sent. So it has to know why M3 was sent only because of sending of M1. So only after it gets M1, it can interpret M3 and process M3. Clear? So this is what is called causal ordering of messages. So what does it mean? If there are two messages like this, where the sending of one message happened before the sending of the other message, then the receiving of a message, which means the delivery, so I may interchange the terms, but actually what I mean by delivery. So the delivery or receiving of the message should happen before the other message. So that's why I do a buffering here. What I mean by buffering here, that the lower layer I talked about. You may receive it, but you have to store it in a lower buffer without delivering the application. And once you deliver M1, now you can deliver your M3. So that's why you have to buffer it, means you have to temporarily store it before you deliver it to the application. Okay? So that's why I kind of show the actual time, the receiving is this line, the dotted line, but you deliver it, after buffering it, you deliver to the process. Is that clear? Okay. So how to guarantee this causal ordering of messages? So we are going to look at three algorithms, because let's look at if you just happen to receive M1 and M3, you see the big picture. But how the process 3 gets to know that something was sent before M3. You know what I mean? The distributed system. So you don't know it's not shared common memory, right? So and M1 is sent to process 3, and M2 is sent, M3 is sent like this. Of course, there's